Hello everyone, we are Group 3 and we're gonna present mechanics of materials and nanoscale. Well, at nanoscale, meaning dimensions between 1 and 100 nanometers, materials behave very differently from what we see at macro level. That is because a much larger fraction of atoms are located at or near the surface, and these surface atoms do not have the same bonding environment as interior atoms. Additionally, quantum effects and atomic interactions start to dominate, and we can no longer assume that materials behave like smooth, continuous objects. This was where classical mechanics begin to break down. These changes of behavior open up new possibilities for engineering materials with better performance, such as stronger nanocomposites, high precision MEMS devices, and even biomed tools at cellular level. One of the biggest reasons nanoscale materials are act differently is because of surface effects. As the structures shrink, a greater percentage of atoms are on the surface rather than the inside material. This results in much higher surface energy, and it starts influencing stiffness, chill strength, and even how material deforms. For instance, copper nanowire might become stiffer just because of a mechanical treatment on its surface. At this scale, even surface roughness or oxidation can change mechanical behavior. These effects are something we usually ignore at macro level, but they are critical when we engineer things like nano devices or coatings. When we analyze large structures, we use classical continuum mechanics, which assumes that a material are smooth and continuous. But at nanoscale, this breaks down. Atoms are discrete, non-continuous, and their individual behavior starts to matter. This is why models like molecular dynamics become necessary. This stimulates how atoms interact, move, and deform under stress. Also, quantum effects such as tunneling or energy quantization starts to influence material responses, which classical mechanics do, does not account for. So, when designing nanoscale systems, engineers need to use different tools and theories that what we are used to for larger scale structures.
For nanomaterials, fatigue and fracture are analyzed through a variety of methods including crack propagation. Crack propagation is the rate at which a crack forms within a material under an applied load, but is highly dependent on the material type. When analyzing brittle grains, smaller grains tend to have higher crack propagation and require lower fracture energies. The inverse could be said for larger grains. Ductile materials, however, act very differently. Due to the Hall-Petch relationship, smaller grains lead to stronger material properties. Grain boundaries are decreased for larger grains, though, making dislocations easier and increasing plastic deformation. For both material types, however, the Young's modulus of the material generally increases linearly with grain size. Some important time-dependent fracture behaviors to go over include creep fracture and corrosion fracture. Creep fracture can be defined as the progressive time-dependent fracture of a material under constant stress. Generally, this stress is due to increased material temperatures. In nanopolymers, creep occurs because of viscoelasticity, meaning it acts viscous like a thick fluid and elastic like a spring. Under stress, it'll stretch while slowly flowing over time. At the nanoscale, this behavior changes since the polymer chains are much more restricted. The second behavior, corrosion fracture, occurs due to a combination of mechanical stress and corrosive environment conditions. In nanocrystalline structures, it's expected that there's an increased corrosion rate due to a mixture of anodic and cathodic reactions. Anodic sites lead to material dissolutions, while cathodic sites increase embrittlement risks. Cathodic reactions can be used to protect nanomaterials as well, though, but it is generally more difficult to achieve since small grain boundaries can bring more anodic reactions, even if the rest of the crystalline structure is protected.
All right, so next we have experimental and computational methods at the nanoscale. One experimental technique at the nanoscale is nanoindentation, which determines the mechanical properties of materials such as hardness and elastic modulus. This is done by pressing a hard tip, which is usually made of diamond, into the surface of a material and measuring the resulting force and displacement. Another technique is using atomic force microscopy. This process uses a sharp tip that moves across a sample surface to create an image. This technique can be used to help determine surface roughness as well as hardness and elasticity. Next, we have scanning electron microscopy, which uses electrons to generate high resolution images of surfaces. These methods can be used to help us understand materials in incredible detail. Another method that can be used would be a computational simulation, such as molecular dynamics, which is used to study the motion of atoms and molecules over time. This can be used to study crystal structures, material defects, and mechanical properties at the atomic level. Another method is density functional theory, which is a quantum mechanical approach that calculates electronic structures from first principles. This can help design new molecules or surfaces with tailored properties. An emerging trend is the use of AI to help accelerate research by sifting through a large amount of data to find patterns a human cannot. Another trend at the nanoscale is nanoscale energy technologies, which are creating efficient systems such as tiny solar cells and batteries. Lastly, sustainable nanotechnology is now being used to help reduce waste and energy at the atomic level.
Nanomaterials play a significant role in enhancing mechanical performance, reducing weight, and improving durability. Their unique mechanical properties, such as high strength to weight ratio, wear resistance, and thermal stability, make them ideal for demanding applications. In biomedical engineering, they offer enhanced mechanical properties, biocompatibility, and functionality for various medical applications, such as nanofiber scaffolds for cell growth and stem cell differentiation. Nanomaterials have also revolutionized the electronics and semiconductor industries by enabling smaller, faster, and more efficient devices. To continue on with applications, nanomaterials are the solution of transforming how we generate, store, and use energy, playing a critical role in developing clean, efficient, and sustainable technologies. For example, in photovoltaic cells, nanowires enhance light absorption and conversion efficiency of energy in solar panels. In structural engineering, nanosilica particles improve crack resistance, and certain concretes can even heal on its own. Nanomaterials are shaping the future of electronics by making devices smaller, more powerful, and more energy efficient. Overall, nanoscale mechanics is driving major innovation across engineering. From stronger implants in biomedicine to lighter vehicles, smarter electronics, and cleaner energy systems, by tuning material properties at the nanoscale, we can create structures that are not only stronger and lighter, but also more efficient and sustainable. As engineers, understanding these size scale effects opens doors to designing the future smarter, cleaner, and more resilient.
At the nanoscale, materials exhibit unique behaviors due to size scale effects which differ significantly from their bulk counterparts. These phenomena offer immense potential for innovation across industries, and I'll be talking about how it affects the next generation materials, AI simulations, and how it is in eco-friendly applications. So first, with self-healing. One of the most exciting developments in the emergence of next-generation nanomaterials, such as self-healing materials, They, for instance, can repair themselves after damage by incorporating nanomaterials like graphene or MXenes. This allows them to restore both mechanical and electrical properties, extending their lifespan. Studies show that self-healing polymers and nanofillers can recover up to 90% of their original strength. Imagine the implications for flexible electronics, wearable technology, and aerospace applications where durability and reliability are paramount. Now, AI and nanomaterial design and control. Another key driver of progress is the integration of artificial intelligence and the advanced simulations into nanomaterial research. AI accelerates the discovery of and optimization of nanomaterials through predictive modeling and simulations. By reducing the time and cost of experimentation while improving accuracy, AI enables us to tailor materials for specific applications, such as medicine, energy storage, and smart infrastructure. For example, AI-controlled robots with nanoscale precision are already being used to create custom designs and provide real-time feedback during manufacturing processes. This synergy between AI and nanotechnology is revolutionizing how we approach material science. For example, if you also look at the image on the right, you can see how nanomanufacturing uh, works with a whole bunch of like AI different control robots, AI in optimizing 3D nano printing, AI driven in additive manufacturing, and AI in quality control. With this nanoscale precision, it will once again benefit in simulations, custom designs, and feedback response. Finally, in how it affects in eco-friendly nanomaterials. Why eco-friendly? Well, traditionally, materials often harm the environment, while nanomaterials can reduce waste and energy consumption. For some examples, biodegradable nanocomposites and sustainable coatings. So if you take a look at the picture on the right-hand side, you can see all the different types of coating techniques that are used to apply like a thin layer of bio-based films from chemical, physical vacuuming, spraying, and hot pressing. Those are just different types of coating techniques. And the benefits of this is, it has lower carbon footprint, recyclability, and a reduced resource use. Finally, these are our references.